So we'll basically use what we understood about the electron affinities and ionization energies to explain why certain atoms like to ionize and form positive ions versus other elements that like to make negative ions, while in some cases some elements will not ionize at all, and in this case you will be interacting with each other in a different fashion than the ionic interaction. And this is what we will understand throughout this chapter. Chemical reactions will only involve valence electrons. And as we learned previously, valence electrons will luckily correspond to the group number of the element. So group 1 will have one valence electron that resides in an s orbital. Group 2, two valence electrons in an s orbital. Group 3, three valence electrons with two in an s orbital and one in a p orbital, and so on. Okay? Those are the electrons that will participate in any chemical interaction. And the first type of interaction is just simply either losing electrons or gaining electrons. Based on our understanding for the metals in comparison to the non-metals, it is gonna be much easier for the metal to lose whatever number of electrons it has to gain the stability of the previous noble gas. Okay? So it prefers losing valence electrons to establish the stable noble gas electronic configuration. And in this case, it's going to be forming a cation. And this is going to be a positive cation. And this is going to be the case for all metals. All group 1 and group 2, 3, all the left-hand side of the periodic table is basically moving from an unstable configuration with 1, 2, or 3 valence electrons to a more stable configuration that corresponds to the previous noble gas to that metal. Okay? And the charge it will have will depend on the number of valence electrons it loses. If it loses 1, it will have 1 positive charge. If it loses 2, it will have 2 positive charges, and so on. On the other hand, non-metals, right here, will prefer to gain electrons. It's way closer to the next noble gas. So once it gains 1, 2, or 3 electrons, it will retain the stability of the next noble gas configuration. And it's easier for it to gain because it has higher electron affinity, as we learned in the previous slides. It prefers to gain electrons and form negatively charged ions, or what we call anions. And the configuration will basically change from an unstable, partially filled electron configuration to the most stable noble gas configuration, the next noble gas configuration. And that explains why elements in the left-hand side of the periodic table like to form cations, positive ions, while the elements on the right-hand side of the periodic table prefers to form negative ions or anions. And you actually can make a prediction about the charge that you expect for each of these ions. Again, it will depend on the number of valence electrons it will either gain or lose. So left-hand side is going to prefer to lose and become positive, while right-hand side is going to gain and become negative. Number of electrons it will lose or gain is going to correspond to the number of valence electrons. For metals, it will lose, and it will lose the number of valence electrons available. 1 for group 1, which will make it +1, or 2, which will make it +2 for group 2, or 3, which will make it +3 for group 3. On the other hand, it is 1 electron away for group 7 from the next noble gas. So that's why it gains just 1 electron and becomes -1. Group 6 is 2 electrons away. So it needs 2 electrons, it gains 2 electrons, and so on. 3 electrons. Group 4 usually doesn't like to either gain or lose. It usually gets in covalent bonding, which doesn't involve any gaining or losing of electrons. Okay, and we'll explain this later on. This part of the periodic table are still metals, which means they actually prefer to lose electrons and form cations, but it's a little bit more complicated because it can lose a variable number of electrons and form a variable number of cations. Whenever you have a combination of two elements that are one metal, like lithium, with one non-metal, the metal prefers to lose and the non-metal prefers to gain. So what will happen is that the metal will lose an electron and become a plus charge, and that electron will actually be gained by the non-metal. So the non-metal will gain that electron and become an anion. And because it's simply a combination of positively charged ions with negatively charged ions, they will electrostatically attract to each other and form a salt or an ionic compound. The driving force for that change is that the metal prefers to lose the electron because of the lower ionization energy and its favorability to gain the stability of the noble gas configuration, which is helium in this case. Non-metal likes to gain electrons to get the electronic configuration of the next noble gas, which is neon. And since those are negative and positive charged particles, they will actually electrostatically attract each other and make an ionic compound. Because of the nature of this electrostatic attraction being a very strong interaction, these compounds will be very stable. They will have very high melting point because in order to melt it, you need to overcome the electrostatic attraction that holds it together. And since the attraction is strong, you will need a lot of energy, a lot of heat to melt it. And it also is gonna be polar, it's gonna be ionic, so which means it will like ionic solvents like water, so it will dissolve in water. And these solutions will conduct electricity because it will contain free ions, and since you have positively charged and negatively charged particles that can move freely, these can carry electric current and conduct electricity throughout the solution. The last thing in the context of ionic interaction is to explain the energetics of that interaction. What is the source of that strong attraction or that strong energetic stability? Is it just the ionization of each species? Because if you react a metal with a non-metal, it's going to actually release a huge amount of energy, which corresponds to a huge stabilization of the compound. It's 411 kilojoules per mole for that reaction. So what's the source of that very high energy here? In order for this reaction to take place, we'll have to do a couple of steps. We'll have to first have all the elements in the gaseous state. In case of the metals, they are usually in the solid state. So the first step is going to be transforming the metal from the solid state to the gaseous state, which is going to require energy. It's going to be melting, which needs energy. And that amount of energy for sodium is 108 kilojoules per mole. Next step is going to be ionizing that gaseous atoms of sodium. Ionization is energy needed to overcome the attraction that the valence electron feels. So again, you need to put that much energy to ionize the sodium atoms to sodium ions. And on the other side, you need some energy to break the molecule of chlorine apart into the corresponding free ions in the gaseous state. And the only step that produces energy is the ionization of chlorine to chloride. That is going to release a little bit of energy. However, we have 3 steps that require energy, 1 step that produces energy. So overall, till you reach the point where you have positive sodium ions combined with negative chloride ions, the energy change is going to be the sum of all these changes. And it's going to actually, in fact, be positive, which means that change, in order to happen, actually needs energy. It doesn't produce energy. So it should not be favorable. It should not happen on its own. It should need you to put energy in so that the change or the reaction take place. So what's the source of energy that provides the energy required for the reaction to take place and even produce some energy out of the reaction in a total amount of energy that equals 787 kilojoules per mole? What's the source of that huge amount of energy? It's actually the attraction force between the ions. The attraction force, as governed by Coulomb's law, is a negative energy change, right? The attraction causes the system to have lower energy, and that lowering or decrease in energy is going to be directly proportional to the charge of the ions. So the larger charge on the ions, the more the attraction is, and it's going to be inversely proportional to the size of the ions. So the smaller ions involved, the larger the attraction will be. That attraction energy is called the lattice energy for the ionic compound. And as we said, it increases with higher charge and lower radius for the ions. And that actually is the source of that huge amount of energy here. That is even enough to provide the needed amount of energy for the ionization to take place and produce an extra amount of energy out of the reaction overall. If you compare a combination of 2 ions with 1 plus charge and smaller size in comparison to 2 ions of the same size but larger charge. Larger charge means higher attraction. Larger size means lower attraction. So the one with the smallest size and larger charge is going to be the highest lattice energy, and the one with the smallest charge and largest size is going to be smaller lattice energy. For each of the following pairs, calcium with oxide versus potassium with fluoride, which one will have larger lattice energy? If you compare the ions, both calcium versus potassium, calcium have larger charge, and also fluorine versus oxide. Oxide have larger charge. So both of the ions involved in the second combination have higher charge, which means higher lattice energy. And even in terms of the size, what's the size of calcium in comparison to potassium? Calcium is going to be smaller, so even in terms of the size, calcium should have more lattice energy because it's smaller.